Welcome to the lesson on methods for improving quality. Upon completion of this lesson, learners will be able to explain the strategies to improve quality in a manufacturing environment, differentiate between the strategies to improve quality in a manufacturing environment, and construct a quality plan that involves various methods of improving quality. Companies realize that there is a substantial return on investment from improving quality practices throughout their manufacturing processes. Successfully emphasizing quality as an integral part of the overall company culture and strategy gives manufacturing facilities an edge in the competitive market as their products face few quality issues. Previously, we have discussed the overall quality management system and quality control. However, it is imperative that the manufacturing facility and its employees understand and become involved in the continuous improvement of product quality. There are 4 strategies commonly used in production facilities to improve quality. They are reducing the number of defects, reducing product variability, increasing first pass rates, and reducing scrap, reworking, and recycling products. In competitive production facilities, these strategies become a primary goal for each employee. The following slides will explain each strategy in detail. A non-conforming or defective product is one that does not meet one or more engineering specifications. Such products are not necessarily unusable or unsafe. However, the longer a defective product is manufactured, the more likely consumer confidence in it will be affected. By understanding and resolving the causes of defects, their numbers can be reduced. Doing so will also increase the productivity of the company and improve customer satisfaction. Variability is often the primary source of poor quality. Variability may be introduced into products at every stage of the manufacturing cycle. Thus, inspection is an important step at each stage of the process to determine that the end products of those stages meet specification standards and that variability is under control. The image here shows 2 processes that have the same mean value but different variability. Can you determine which process has higher variability, which results in less scrap or rework? Process 2, depicted in green, exhibits a higher variability among its products. Process 1, depicted in gray, thus results in less scrap or rework. Determining the causes of variability can be a long process as it is affected by various factors. The quality of the raw materials, the storage and handling procedures, faulty or old equipment, equipment that cannot meet acceptable tolerances, and insufficient training. First pass rate is defined as the number of acceptable products, those not needing rework, divided by the total number of products resulting from a process over a specific period of time. While it is expected that not all products from a particular process in a manufacturing facility will conform to engineering standards, first pass rates can be improved through quality control methods. Statistical techniques may be helpful in improving this metric. Pareto charts can also help increase first pass rates by determining the most common defects seen in the process and focusing on reducing them. Similar to variability, other factors such as the quality of raw materials, the storage and handling procedures, faulty or old equipment, equipment that cannot meet acceptable tolerances, and insufficient training can affect first pass rate. Improving quality through the reduction of defects and variability and the improvement of first pass rates will probably result in fewer scrapped, reworked, or recycled products. A product is scrapped or discarded when it is not salvageable. A product is reworked when it is salvageable but requires additional processes to remain in production. And a product is recycled when the whole of it or some of its parts can be modified for other purposes. The figure here shows the 3 types of non-conforming products. When a manufacturing facility is experiencing excessive scrap, rework, and waste, it is crucial to first determine the source or cause of the majority of the problems. Having a detailed sampling plan and quality checks at critical processes can help reduce scrap, rework, and waste. An efficient sampling plan not only helps technicians detect these issues, but also determines if the process needs to be shut down to investigate the source of the problem further. However, in some instances, large amounts of scrapped, reworked, or recycled components are a symptom of another problem. For example, an electric vehicle battery manufacturer wants to reduce the number of battery modules being rejected during final assembly. Upon further inspection and sampling, a quality control team discovers that the rejected modules are not actually defective. finding that 60% of what the assembly operators are marking as faulty are actually within specifications. Through subsequent investigations, they learned that the automated battery module placement system is operating at a rate too fast for operators to properly conduct visual inspections and connectivity tests. The solution is to adjust the automation speed to match human inspection capabilities and retrain the workers on proper inspection procedures at this optimized rate. Return on investment, abbreviated as ROI, is a performance measure, usually in terms of money, that is used to evaluate the efficiency of a company's implementation of a method or group of methods. Return on investment can also be described in terms of time and yield. The result of implementing quality improvement strategies will, in turn, improve overall manufacturing yield and customer satisfaction. This increase in productivity and improved customer relations will impact the confidence in the product as well as its availability. The illustration here depicts these quality initiatives and their returns on investment. Quality problems often occur after product development and during its manufacturing or assembly. Engineering changes can, in turn, have implications for product delays, quality issues, and retraining costs. Design for manufacturing, abbreviated as DFM, and design for assembly, abbreviated as DFA, are two methods for avoiding potential problems after product development. These methods integrate product design, product manufacturability, and product assembly into one common activity. On this slide, you can see the 9 guidelines typically followed in design for manufacturing and design for assembly. We will explore each guideline in detail in the upcoming slides. Reduce the number of parts. By reducing the number of parts in the manufacture or assembly of a product, the company will make fewer purchases, have less inventory, reduce processing and development time, reduce equipment, reduce handling, make assembly easier, and spend less time on inspection and testing. Develop a modular design. Using modules in the design of a product simplifies such manufacturing activities as inspection, testing, assembly, redesign, and maintenance. Use standard components. Utilizing standard components as opposed to custom-made ones can not only save money but also prevent the unforeseen delays that custom-made items can cause. Design parts to be multifunctional. Multifunctional parts are those that serve 2 different functions in one product. They not only help reduce the number of parts but also save assembly time. Design parts for multi-use. Multi-use parts are those that can be used in 2 or more different product lines. They help reduce the number of parts in the overall system and minimize the number of categories and the variation between parts and products. Design for ease of fabrication. Designing for ease of fabrication involves selecting optimum combinations of materials, fabrication processes, and skills requirements to minimize the overall manufacturing cost. In some cases, excessive tolerance and surface finish requirements add unnecessary production costs and should be avoided if possible. Minimize assembly directions. As part of the design for assembly, it is suggested that all parts be assembled from one direction, preferably from above in the vertical direction and parallel to the gravitational direction. Maximize compliance. Compliance refers to visual and tactile elements that aid in the assembly of a part, helping to prevent damage resulting from improperly combining 2 parts. These features include tapers or chamfers in moderate radius sizes for facilitating insertion. And lastly, minimize handling. Product or material handling is one of the easiest places for removing unnecessary waste from the system. It can also aid in the reduction of damages due to improper or excessive handling. Handling also involves the safe packaging of the final product. Using these methods will result in a product that is easy to manufacture and assemble. If more time is spent during the product design process by using design for manufacturing and design for assembly, there is a potential for capital savings for the company on the manufacturing side. The ISO 9000 family is a set of standards recognized worldwide for quality management systems. ISO 9004 provides guidelines for establishing a standard of continuous improvement at the organizational level and for customer satisfaction. Improvement activities that ISO 9004 outlines and suggests for sustained success include a long-term planning perspective, constant monitoring and analysis, identification of short and long-term risks, and anticipation of future resource needs, among others. The organization should define objectives for the improvement of its products, processes, organizational structures, and management system through detailed data analysis. ISO 9004 suggests that the organization follow structured improvement processes such as the Plan Do Check Act, abbreviated as PDCA methodology, which will be discussed in detail in this module. ISO 9004 also suggests that a successful organization ensures that continuous improvement becomes a part of the organizational culture. This goal can be accomplished by providing employees with opportunities to participate in improvement activities, providing the necessary resources, establishing recognition and reward systems for improvement, and emphasizing continual improvement of the effectiveness and efficiency of the improvement process itself. Dr. Yoji Akao, who originally developed quality function deployment, abbreviated as QFD, in Japan in 1996, described it as a method to transform user demands into design quality, to deploy the functions forming quality, and to deploy methods for achieving the design quality into subsystems and component parts, and ultimately to specific elements of the manufacturing process. In other words, QFD is a method for identifying requirements critical for the customer and for creating a link between those customer needs and the design parameters of the product or service. Dr. Akao combined his work in quality assurance and quality control with the function deployment traditionally used in value engineering. The primary goal of QFD is to align product requirements with market segment perspectives, company capabilities, and technological demands. Additionally, it assists organizations in establishing priority hierarchies for characteristics when determining target values. The end product of this method is a group of matrices often referred to as the house of quality depicted here. By looking at the market segments and company or technology needs, QFD helps give voice to the customer through engineering and quality characteristics for a new or current product or service. This method also aids in the prioritization of these characteristics when developers are setting target values. This method is used more often by the quality department than by production technicians. However, it is an important tool to understand as more companies require participation from all levels of the team to resolve quality issues. Kaizen comes from the Japanese words kai, which means to change or to correct, and zen, which means good. Translated, Kaizen means change for the better or improvement. A method of continuous improvement in product quality, processes, productivity, and all-around company culture. Kaizen is a system that involves all employees, encouraging them to contribute to the company's mission with small improvement suggestions on a regular basis. Kaizen involves setting standards and then continually improving them. To support the higher standards, Kaizen also involves providing the training, materials, and supervision needed for employees to achieve the higher standards and maintain their ability to meet those standards on an ongoing basis. The concept of zero defects is a way of thinking and doing rather than a methodology that will accomplish zero defects. It establishes a company culture in which defects are not acceptable, meaning the focus is on producing the product correctly the first time. It also reinforces the idea that if you have zero defects, you're able to increase profits, eliminate the cost of failure, and increase customer satisfaction. Even though zero defects do not have distinct steps, rules, or guidelines to follow, it can be an effective philosophy as it is adaptable and flexible to any situation, business, profession, or industry. It is often discussed whether the goal of zero defects is attainable or if it sets users up for failure. However, zero defects is not about perfection, but about changing expectations and focusing constantly on the goal of improvement. If zero defects become part of the company culture, employees, in turn, will be able to recognize the high cost of quality issues, continuously think and investigate causes of defects, and work to address the flaws in the processes that allow defects to occur. Kaoru Ishikawa, a professor at Tokyo University, developed the idea of quality circles. Quality circles, introduced into the United States by Joseph M. Juran, include teams of employees at every level that drive the organization's mission of quality. They are associated with two primary tasks: identification of quality problems and suggestions of solutions for the problems identified. The next slide explains a list of guidelines to be followed to establish a productive quality circle. To establish a productive quality circle, the following guidelines should be followed. Assign employees at all levels to a quality circle. Appoint a chairman. This chairman position can be rotated among the team members. Prepare an agenda before the meeting, conduct organized meetings, appoint a recorder to take minutes, and set action items before the end of the meeting to be discussed first at the following meeting. Quality circles work best when they are supported, encouraged, and provided resources by senior management. Participants also benefit by learning through peer-to-peer interactions. The Taguchi methods are statistical analyses developed by Dr. Junichi Taguchi to improve the quality of products and provide consistency of performance in order to reduce variation in products by identifying key product characteristics. He clarified that variations led to such defects as poor fit, poor finish, oversized products, undersized products, scrap, rework, warranty claims, and most important, loss of customer goodwill. Dr. Taguchi's three methods include the Taguchi loss function, offline quality control, and innovations to the design of experiments, abbreviated as DOE. The three methods are explained in detail in the following slides. The first method is Taguchi loss function. Dr. Taguchi explained that any variation from the specifications of a product causes loss. To make his case to organizations, he associated this loss with a cost value. Based on his loss function, Taguchi said that the variations or deviations from the target value led to a loss that was exponential in relation to its distance from the target. The method addresses three types of quality targets: larger the better targets, where characteristics need maximization, as seen in agricultural yield; smaller the better targets requiring minimization, such as toxic pollution reduction; and nominal the better targets demanding specific values, such as achieving precise widget diameters. The figure you see here shows the nominal the better loss function. As this figure shows, the loss, marked in gray, increases as the product lies further to the left or the right of the target value. Taguchi also advocated for offline quality control, methods that look at the entire system rather than the individual products and processes. The three methods for offline quality control are system design, parameter design, and tolerance design. System design analyzes the entire collection of processes, focusing on redesign through creativity and innovation. Redesign can be done at the conceptual level of a new product line or for a specific purpose. The hope is that innovative ideas will evolve, resulting in appropriate changes in the system. The goal of parameter design, the next offline quality control method, is to identify the appropriate parameters of a product that make its performance less sensitive to uncontrollable factors such as environmental variables, deterioration, and manufacturing variations. It aids in the reduction of variability caused by these external factors. Therefore, time and energy are not spent trying to control them. Finally, tolerance design is aided by both system and parameter design. Once variability from external factors is removed, further attention can be placed on understanding other potential sources of variability and tightening the tolerances of a product. Dr. Taguchi's influence on the design of experiments has brought him both praise and criticism. Practitioners are often the proponents of these methods as they provide the opportunity to consider a large number of factors that may influence a quality characteristic and determine which are significantly impacting target values. Previous methods required large amounts of data. However, Taguchi's methods require fewer data points. Much of the criticism of his methods in the design of experiments comes from academics and those supportive of complete theoretical methods. They see his methods as incomplete and not well defined. Benchmarking involves comparing one company's performance metrics to another's, to industry best practices, or to best practices from other industries. This process can help a company meet its quality goals by comparing itself with other competitive, world-class companies, especially important in today's global market. Benchmarking can be done within the company, with other companies, and with other types of industries. For example, let's look at this hypothetical scenario where an EV battery assembly line at a company site in Detroit produces 100 battery packs per day with a first-pass quality rate of 88%. However, there is a similar assembly line in Austin producing 100 battery packs per day at a first-pass rate of 97%. Such an internal benchmark provides the company with a clear picture of line performance variations. With this information, managers from both locations can meet to discuss how and why the Austin line achieves higher quality rates and implement appropriate improvements at the Detroit facility. Benchmarking products and processes can help determine and drive the quality goals of the company. In summary, Organizations must employ multiple key strategies to improve and maintain quality, including defect reduction, minimizing product variability, improving first-pass rates, and decreasing scrap, rework, and recycling needs. These objectives are achieved through various quality improvement methods such as DFA, DFM, ISO 9004 guidelines, QFD, Kaizen, zero defects, quality circles, Taguchi methods, and benchmarking. Success in continuous improvement demands total organizational commitment to enhance quality, yield, and customer satisfaction while managing costs. Manufacturing technicians play a critical role by understanding and supporting multiple quality initiatives, recognizing that no single method alone can resolve all manufacturing challenges. Thank you.